Hi, everyone. I am Tyler Richey-Yowell, and I am, as Allison said, in the Percival Lowell postdoctoral fellow at Lowell Observatory in Arizona. So good morning. I'm really excited to get a chance to speak to you guys today, and I'm really looking forward to any kind of discussion that can come out of this. So I really want to first thank the organizers for having me, because I'm really excited to talk to you guys. So the super big picture question that inspires my work actually starts with the search for life on other planets. But how do we actually go about finding life? And so ideally, if we had unlimited time and resources, we'd search for life something like this. You know, we discover a rocky planet. We check if it's in the habitable zone, which is just defined as the temperature where water would be liquid. And then if it is, we go and look at its atmosphere to see if there's molecules that would be indicative that life is potentially there. In reality, though, you guys know that it's not feasible for us to observe every planet that's out there. So we have to have some way to prioritize which targets we actually want to spend the time observing. And true habitability isn't just defined or guaranteed by a planet being in the habitable zone, though. So it's a lot more, there's a lot more that actually goes into being able to form life. And so the major components that go into this are stellar effects, planetary system components, and the properties of the planets themselves. And of course, each of these can be divided further into subcategories that each play a role as well. And so my research focuses on understanding the potential from life to form from the stellar side, that is understanding the spectra of stars, the stellar activity, and the luminosity evolution of the star. So this kind of tells us how much radiation is actually incident on the planet. And so to kind of rephrase this, in order to understand planetary habitability, we need to know how does the flux of a host star evolve in time. So some of the most important wavelengths for determining planetary habitability, at least from the stellar perspective, are those at high energies. So what happens at these wavelengths is that you can drastically alter your atmospheric chemistry. So here we have a spectrum of a late K star, and you can see that most of its peak is in the black body, or sorry, most of its flux is in the black body peak here in the infrared. And so if we kind of zoom in on this left side here where the UV and the X-ray are, we can see that there is actually flux there, even though it's quite small. But the UV will photodissociate molecules that are necessary for the development of life, such as oxygen or water, and signatures that would potentially be indicative that life may be there, like methane or ammonia or nitrogen oxide. Whereas the X-ray and the extreme UV will ionize the atoms and may cause even complete erosion of the atmosphere. So not too good if you're trying to live there. So even though these features are quite small relative to the black body peak, they are still quite important. So what we really need to know to understand planetary habitability is how the stellar high energy radiation evolves during a timescale where planets are forming and their atmospheres are still stabilizing. What kind of host stars do we want to look at? So studies about habitability have mainly focused on M stars, as these are our smallest and coolest types of stars that live for a long time, and they're easy to observe planets around because of the low contrast between the planets and the star. G stars or solar type stars like our own, on the other hand, have shorter lifetimes and are harder to observe planets around. But obviously we have one detection of life there, so something's got to be working. But then there are K stars, which have often been neglected in these studies and might be similar enough to G stars, but have the observational advantages that M stars have. So these might be the Goldilocks of host stars. In fact, K-stars might actually be some of the best candidates for hosts of habitable planets. So Kunzingen in 2016 determined a parameter to essentially estimate the probability of a certain temperature of star to host habitable planets. So anything above the probability of a G2V star like our own hosting a habitable Earth-sized planet is what we define as super habitable, or giving better conditions for life to form than even Earth had. So while this does actually peak in the late M stars here, we've recently seen through studies of M dwarfs that not only do M stars flare more often than our sun, but they can exhibit super flares or flares with larger energies than the largest solar event ever recorded. And that can happen on the order of once every 1 to 10 days. And as I showed earlier, all this high energy radiation may not actually be good for planetary life. And so this might actually exclude this region, these late M stars from being good hosts. And so you can see that the next peak is actually in the early K-dwarf regime here. And it actually remains quite high and above even this super habitability threshold here throughout the whole K-star spectral type. But when I started working on this project, we didn't know what kind of high energy environments that K-stars provided as a function of time. And so that's where I came in. So I wanted to know what the high energy evolution of K-stars looks like. And I expected it to fall somewhere between G and M stars. And so for G stars, when we look at how the X-ray flux as a function of age evolves, we see that G stars decline by at least 100 mega years if there's even any period of constant flux at all before this decline. And early M stars, on the other hand, have been observed in both the UV, so these black and red points, and the X-ray to decline after a saturation period or a period of constant flux of about 150 mega years. So what about K-stars? Well, it kind of makes sense that they would be someplace in between G stars and M stars. And so I expected them, I think we all kind of expected them to decline someplace between 10 and 150 mega years, which seems like a good assumption. So besides the photometry I just showed, we have seen in spectroscopic works that M star UV flux evolves considerably between young to, my colors are wrong. So the blue is the young, the yellow is intermediate age, and green is field age M stars. And so we definitely see a clear evolution between these ages for M stars, which has been shown in some recent papers to definitely play a role on the chemistry of the planetary atmospheres. But what does this look like for K-stars? Well, I decided to find out. So I led an HST proposal to study K-stars of the same ages as that previous study so that we can make direct comparisons. So a young and intermediate and field age K-stars that we looked at. And so these are just three examples from this study, and you can see something very different from the M dwarfs here. So there's actually appears to be no evolution between the young and the intermediate age K-stars, something very distinct from the M stars here. And so as well as comparing the broadband characteristics of the spectra, we also want to look at the specific spectral lines that probe the chromosphere and the transition region of the stars and see how those evolve in time as well. So if we take magnesium-2 here, for example, we can measure the surface flux from the line and plot this as a function of age. These flux evolutions are typically presented as a region of constant flux, followed by a power law decline. And we can see here for magnesium-2, this decline isn't super sharp, but there might be something there. And other than magnesium-2, we've done this for these other 7 spectral lines in the far UV, as well as measuring the decline or the evolution of the near UV continuum and the far UV continuum. There we go. But what's really interesting is when we actually compare this to the M stars. So we see that K-dwarfs actually appear to have a prolonged saturation period or longer period of constant flux before starting to decline. Whereas M stars, it's after about 150 megayears. So the K dwarfs are actually radiating more UV flux at these intermediate ages than M stars do. While the evolution for M stars is well known and is definitely somewhere around 150 megayears, we can see that there really isn't any constraints on what age K stars do actually begin to decline in their UV activity. So I don't want to overwhelm you with a ton of plots. So I've just shown a subset of the other lines here. And you can see that they follow kind of the same trends as the magnesium-2, with a period of constant flux out through or beyond 625 megayears, followed by a decay. And in each of these instances, there appears to be a prolonged saturation period. Another important factor to look at is how the UV changes with rotation period. So we see that for the far UV lines, which are all of them, but magnesium-2, the period of decline is actually nearly the same as for early M stars. And if we normalize the rotation period by the convective turnover time of the star to get the Rossby number and compare K and M stars on a more similar basis, we see that a similar story for the far UV. In the near UV, it's a bit more drastic that there really isn't much decline going on at all for the K stars. So we do see a bit of a wavelength dependence on the age of decline. So I had these results and I was like, what the heck is going on here? This is pretty contrary to what we thought would happen. And so around the same time, when I was looking at these results, was when this work by Jason Curtis came out, and a bit of a light bulb went off where I was thinking, oh, maybe these two things are actually related. And so this plot from his paper shows rotation period as a function of effective temperature of the star for stars in clusters of different ages. And so overlaid on these, get the plot to go. Overlaid are these are current gyrochronological models of where we would expect stars at this age to fall within this rotation period versus effective temperature plot. So you can see here that these models match up pretty well for G stars. So the green line is on top of the green points for G stars and the red line on top of the red points, and that there's clear evolution. So there's a difference between the orange points and the green points here. So the orange are 670 megayears and the green are 1 gigayear. Whereas for the K stars, we see no rotational evolution between these ages. These points are overlapping, whereas we would expect the green points to be up further at slower rotation periods, and same with these red points here. So we're really seeing no rotational evolution for K stars. And this is an effect that they're calling K-dwarf rotational stalling, where the rotation spin down of the star appears to stall. So there's a few theories as to why this is happening, but the current leading model is through what we call core envelope recoupling. So this considers the star as a two-zone model. So you have a core and an envelope. So when the star is young, it's rotating as a solid body and spins up as it contracts onto the main sequence. But once on the main sequence, though, the magnetic braking reaches kind of a maximum efficiency. And so the angular momentum transport from the interior core to the outer envelope can't quite compensate for the rate of mass loss at the surface. And so you start to build up this increased differential rotation between the core and the envelope. And so at this point, there's a spin up torque from the core trying to balance out the spin down torque from the stellar wind. And so these two torques kind of can balance each other out so that you get a temporary stalling of the rotational spin down on the star. And so the rotation remains roughly constant. After enough time, the angular momentum transport is essentially able to catch up though. And so the core and the envelope once again begin to rotate as a single body and spin down resumes. So this is kind of what we think is going on here. This really seems to be happening for K stars. but is kind of mass dependent. And so now, because we know rotation and activity are correlated, we should expect longer elevated rotation rates to mean longer elevated UV flux. And if we bring up my results again, we see that for K-stars, there's no rotational evolution before about 2 gigayears, contrary to what is happening for the M-stars. And we see nothing very different in the rotational evolution between M and K stars, and that rotation decline is somewhere around 10 days as well. So this does seem to be a consistent yet independent picture of what is happening in K stars. So I realized there weren't a ton of spectroscopic data available for that study. So I wanted to look at this through photometry to confirm and have a more robust, broader study. So we actually used data from GALEX of nearly 2,000 K and M stars and plotted their near UV, far UV, and X-ray evolution, so as a function of age. And I don't want you to focus on all of these points. I know there's a lot of points up there, just the turquoise diamonds here, which represent the median flux for each of our age bins here. So if we take these median values and plot them on their own, it's then a far easier comparison between the K and M star data. And I just wanted to show you that there's a ton of data going on here behind these individual points. All right, so these are the same median points from the last plot, just plotted on their own. So here you have near UV as a function of age and far UV as a function of age for K stars, early M stars, and late M stars. So we can see that each of these has a clear, distinct, separate evolution from each other in the near UV and the far UV. And the prolonged period of saturated activity for K stars means that by field age here, your K-star flux is at least 10 times larger than even the early M-star flux in both the near UV and the far UV. But what we really want to know, though, and what's important for the planets, is what the flux looks like in the habitable zone of planets around these stars. So if we take these intrinsic fluxes and see what this would be at the habitable zone distance from the star, then we can calculate the flux in the habitable zone. And so here you have on the right, the habitable zone flux as a function of age. And so we can see now that these fluxes are all overlapping in the UV. So what we've learned is that there actually isn't a big difference in the UV radiation between K stars and M star, or between a K star and an M star habitable zone planet in both the near UV, and it's the same story in the far UV as well. So while K stars have kind of been trying to gain popularity as Goldilocks host stars, balancing the advantages and problems of solar and M stars, we see that at least in the UV, there's really no advantage in the UV for K stars compared to M stars. In the X-ray, though, we actually see that the intrinsic flux here is quite similar between M stars and K stars, which means that in the habitable zone, we do see an order of magnitude lower flux for K stars than for late M stars. So comparing all of the intrinsic flux evolutions, you can see more clearly that there is a wavelength dependence to the age of K-dwarf decline that M stars don't show. So while M star flux consistently decreases by about 150 megayears at each of these wavelengths, the K-dwarf flux declines first for the X-rays by about 45 megayears, then at or beyond 650 megayears in the far UV, and within the scatter of our points, or these error bars here, that near UV is really not declining much at all. And so we see this different evolution just basically means there's a different evolution at different depths within the star, essentially. Since X-rays trace the coronas of stars The far UV is mostly tracing the transition region, and the near UV comes from the upper chromosphere. So the evolution of these regions are different for K-stars. And we've done a lot of comparing to M-stars, but I guarantee there's at least one person in the room thinking, but what about G-stars? Well, unfortunately, there's really no direct comparison study for G-stars, but there has been a project called The Sun as a Star by Ribas et al. 2005 that we can kind of extrapolate from in order to estimate. And so these 6 panels show the habitable zone flux for G-stars as a function of age. And they're broken down by wavelengths regimes, which you can see in the bottom left-hand corner here. So if we take the highest wavelength bin and compare it to our data on the left here, we can see that the EUV flux from the evolution of G-stars is about similar to the K and M-star FUV flux, which means that the G-star type FUV evolution probably, it's a little hand wavy, looks something like this. Or about an order of magnitude lower than the K-stars and M-stars. We have a bit more of a direct comparison for the X-rays. So since our study covers basically these top 3 panels combined, we can take this middle one and plot it on its own here. And we see that the G-star X-ray flux is about an order of magnitude smaller than the K-stars, which is about an order of magnitude smaller than the late M-stars. So K-stars are definitely closer to Earth life-forming conditions. So I kind of got through this pretty quickly, but that means more time for discussion, which was great. So K-stars show unique evolutions with wavelength. K-stars do exhibit a prolonged period of saturated UV activity compared to M-stars, which is consistent with independent analyses of rotational spin-down stalling. But what we really found is that the habitable zone planets around K-stars receive similar UV but lower X-ray fluxes compared to those around M-stars, which means that there's no K-dwarf advantage in the UV compared to M-stars, but there is in the X-ray. So kind of a mixed bag in terms of like if K-stars are have an advantage in the high energy radiation regime. So I'll leave it up to you guys to decide, because you know, there's so many things that could be involved, like magnetic fields that could help prevent the planet. So or the planet from evaporating because of all these UV and X-ray radiation coming from it. So really, this is definitely no distinct conclusion about whether K-dwarfs or M-stars or G-stars are better, but just some more part of the bigger pieces of the picture to fill in. So cool. Well, with that, I will take any questions.
Thanks so much, Tyler. Round of applause. Are there any questions in the chat, or feel free to raise your hand or just unmute?
Oh, I see Sean said, yes, what about the G-stars?
Yeah. I have a question to start. Could you go back to the sun as a star slide?
Yeah.
I guess earlier when you were comparing the FUV and the EUV. Yeah, here, are you scaling? Are you using some scaling between FUV and EUV, or how are you?
No, this was just kind of from looking at some K-dwarf spectra. It seemed to be kind of consistent that the EUV to far UV was maybe about an order of magnitude difference, because it really does depend on the star and what specific spectral type, even within K-stars. So this was me just trying to say, oh, it's probably here. But if anyone does know any far UV studies for G-stars, please let me know, because I think that's really valuable information to have as actual data besides kind of this hand wavy thing. And I'm sure that there definitely are scaling relations that I could have used. But really just to kind of make a point in this talk that the K and M stars are probably different from the G stars.
Yeah, so is the difference here like those sun points you're showing, or is that mainly just scaled by the habitable zone distance for G stars?
Yeah, so I've covered it up here, but the flux, this is the flux density at 1 AU. So this is,
Okay.
so these are all scaled by the habitable zones. Yep.
Okay. Jessica had a comment in the chat. Thank you for explaining what the different wavelengths measured and how they point to different parts of the stars. Michael says, is there Galax FUV data for G stars?
Yeah, so that is something that my team has been considering doing. So the first study was HAZMAT, or the Habitable Zones and M-star Activity Across Time program. And then I did the HAZCAT, so the K-stars, and we've thought about doing a HAZGAT, but hasn't quite happened yet. So, but I think that is really where we need to go next, just because like G stars are important. We do have one detection of life there, so something does have to be working, and so I think that is definitely a study that needs to happen and can happen for sure, like right now. So just got to get the time.
Any other questions from the audience? Yes, Michael says would be good to know if our star is unique.
Yeah, for sure.
Yeah, Jessica, I see your hand raised.
Uh-oh. Hi. Hey.
Hi, Jessica.
Hey, Tyler. Good to see you again.
Yeah, you too.
I have a very silly question, and it's because I'm not a stars person at all. As these stars decay in different wavelengths, what does that mean in terms of like the star's output and activity, and have, I'm not even sure what it is that I'm asking. I think I'm mostly trying to ask, like, what's the timeline, and can you speculate on the timeline for habitability for these kinds of stars? Do they become less active as they decay? Is there some kind of correlation between activity and I don't know, flux in the UV? I have no idea. Yeah, so in terms of, I think the first part of your question was kind of like input into the planet. And I have a plot that I didn't put on here and is not on my new computer yet, but it's actually going and kind of integrating. If I go back to, let's do these, come on. If I go back to, let's look at this far UV one here. So here's the flux in the habitable zone as a function of age. Or actually, we can look at this intrinsic flux as well. And so like in terms of intrinsic flux coming from the star, like if you kind of integrated under this curve, then you would see that the output from the stars themselves is, I think it was 13 times more for K stars because of this prolonged saturation period where you're getting more flux coming out of the star, and like that's what's going to be input into your planets. So you're getting more flux coming out of the star for longer periods of time, and so that drastically kind of adds up, because this is in log scale, and so this is like 1 billion years by this point. Your K stars basically have the same amount of flux and same amount of activity that they had when they were younger. Whereas for the early M stars here, the activity has decreased by almost an order of magnitude. And so kind of the sum total of the flux that has been output from the star is much, much greater for K stars. And I wish I had that plot. Sorry, I'm happy to email it to you. And so, yeah, I think for the second part of your question, yeah, so the
in this case, I've kind of been using activity and far UV flux to be the same thing for this talk. So yeah. Cool.
Any other questions?
Lost the chat. There we go.
I guess I noticed that the red and the orange that you're showing on a lot of these plots, that's fully convective and partially convective M stars.
Yes.
So do K stars act more like partially convective M stars than fully convective M stars, or do you see kind of points of comparison?
So we definitely see that in terms of like flux, the K stars are definitely closer to the early M stars, or so the partially convective stars. And in terms of rotational activity, we don't, so like even if I go back to this plot, so like this is for early M stars, and we don't have a similar study for late M stars, not yet. And so we see that there is definitely a difference between early M stars and K stars, but we don't really know what's happening like rotationally, what's happening to the late M stars. And there's a lot of people currently working on this, and I've seen some like recent stuff trying to get more data on late M star rotation rates. But it does look like this kind of K-Dwarf, or this rotational stalling does actually, like when you kind of zoom in, there is still a little bit of separation between like early M stars. But some recent work has shown that this does appear to actually like completely combine. So there is evolution. Sorry, let me think of a better way to phrase that. The core envelope recoupling that's happening obviously requires a core and an envelope. And so when you have these fully convective stars, you don't get this anymore. And that is actually what we're seeing within the rotation rates as well. So to summarize, we really need more data about late M stars, but it is looking that K stars are dissimilar from early M stars, but still closer to each other, at least activity-wise, than for late M stars. So great question, thanks.
Yeah, thanks so much. That's pretty interesting. I don't see any other hands or questions in the chat. So we can thank Tyler again. Applause. And yeah, we can wrap up a little early, and thank you so much again for sharing your work, Tyler.
Yeah, no, thank you guys for having me. So
of course.
Really
okay, great. Thank you everyone, and have a great day.
Bye.